think we should start. First of all, thank you very much, Lucas, for setting aside this time for sharing with us, to share with us all your experience in open source, open hardware, low field, etc. We're really fortunate to have Lucas here with us. He did his PhD in Berlin, working, I understand, in ultra high field applications, which is a little bit ironic now that we're going to talk about low field. He worked in the center, you correct me if I don't pronounce it correctly, the Max Delbrück Center in Berlin. And now he's a staff scientist in the Physikalisch-Technische Bundesanstalt, which I think it means National Metrology Institute or something like that. So thank you, Lucas. Please go ahead. I think that you have permission to share your screen if you like.
Mm-hmm. Thank you very much, Pablo, and thank you, Tobias, for the kind invitation. Now there's just a second because the slides are now shared on the wrong screen. So okay, can you see my slides?
No, only the background of Windows.
Okay. Is there a delay? Otherwise, just a second.
Yeah, we see your mouse moving.
You still see just the background of Windows?
The background of Windows?
Can you Tobias, can you stop my sharing, because I somehow don't find the unsharing button. I don't know why it disappeared.
What happens if I share? If I say share, then probably yours goes away. Okay.
Yeah. Okay. let me try that again. I'm sorry for that.
Yeah, Zoom is always a bit weird. Now I don't see my button either.
Okay. So let me try that again. Okay, now you have to stop your sharing that I can share.
I have the same exact problem. The menu of Zoom has kind of disappeared. Okay, wait.
Okay. So, but now we have a problem because I cannot stop.
So in the menu, I can still see it. So if I go into the main menu, stop share. So just this floating menu didn't appear.
Okay, let me try it now. Okay, can you see?
Yes, now we see your.
Yes.
And now I hope that it will, of course. Why does it appear?
On the very top in the orange area, the left there is the presentation.
Yeah, just a second. Okay, can you now see the presentation slide?
No.
Background.
Windows background.
Okay, how can I?
So if you, when you share in Zoom, it should normally ask you what you want to share. If you want to share your desktop or a particular window, maybe you can just share the
Yes. Yes. Can you unshare again?
Yes.
Because
Tobias, in the menu you can do stop sharing.
For me, the button again, it somehow disappears.
Okay. Yeah. That's all right. It's weird. I think maybe there was a Zoom update as usual, and maybe that messed it up.
Just a second. I will try to change the monitor on which the presentation is displayed, and then it should work. Okay, and do you see it now?
There you go.
Yeah,
perfect.
Okay, sorry for that.
No problem.
I have like 3 screens at the moment, and it's a little bit was somehow confusing to Zoom.
Great.
Okay. Good. Sorry for the delay. I will try to speed up to catch up on time. So first of all, thank you very much. Hola, buenos dias. And I will talk about open source low-field MRI and the roadmap to the clinic. So I'm Lukas, and I'm working at the National Metrology Institute in Berlin. I didn't leave completely the ultra high field part. So one side of me is working on MR safety across the fields, and another side is working on this very fantastic project of building an open source low-field MRI and getting it into the clinic. All right, so I have nothing to disclose. I would like to try to do the split a little bit in this presentation, to not go too detailed, but to provide a little bit of MR related information for some of you that might be a little bit more into the topic. So if you have difficulties with some of the parts, please stick with me. There will be different more general topics. I will start the presentation on basically how to build an open source low field MR system. Then I will speak about why low field is interesting and why open source is interesting, and what are basically our next steps in the project. So first of all, just to clarify what open source actually means. So because it's typically not universally understood. So for open source software, which is a little bit more established, so open source software is software that can be freely accessed, used, changed, and shared by anyone. And open source hardware similarly grants the 4 rights of open source, which is the right to study, right to modify, right to distribute and sell, and the right to make. So you can also sell products from that. It's not only restricted to a non-commercial use. You basically have all the freedoms to do it. Bottom line is that these rights are granted non-exclusively. So basically everyone gets these rights. And this is the big idea behind it. All right, so how did we start it? So basically around 2016, we had this very naive idea of saying, okay, we need an open source machine. And this was also the day when the open source imaging initiative launched and started. And in the beginning, there was just the idea, and we gathered community around to actually start working towards this idea. So we have this platform where we post open source hardware and open source software projects around the MR community, because this is an additional incentive to give to the researchers that are sharing actually their code or their designs, that they get visibility, then hopefully get some more citations and are motivated to also share their work. And then a few years later, there were first in vivo images of prototype scanners in this low field system. So this is this very nice work from in particular Leiden University Medical Center, which is not completely based on open source components, but mostly and going into this direction, and a collaboration with TU Delft. And there are some very nice first in vivo images. I will come to that later. And where we are today is we have some more refined prototypes where we are trying to or preparing the open source documentation for them, which we call OSI². Okay, so I have one slide on how MRI works. I included that. I know you had last week this seminar. Just I think it's important when we go through the modules, and I think it's more fun if you more or less grasp the concept. So one thing we need is we need a magnetic field, and what happens? We have a lot of atoms, and they have spins and some magnetic components. And the nice thing is, if you add a magnet to it, then you basically get some magnetization vector here, this big arrow in the center, and the whole thing rotates around this magnetic field. So now in the second step, if we add a radio frequency pulse, which we call B1, so we just need an antenna, we add a radio frequency pulse, and now we can play around with this magnetization vector. If we switch it off, it starts to relax back into equilibrium, and then this depends on tissue, so we get different relaxation times, different tissue contrasts. Then we add another thing which we call a gradient field. So you can think of something like an induction cooker, yeah, just that generates another magnetic field. And because this all rotates in this around this B0 at a particular frequency, now changing the magnetic field slightly, we can change its frequency components. So you can imagine you get a lot of different frequencies. And then basically the last step is some mathematics where you translate these frequencies into an image. And of course, the more frequency components you have in there, then the more details the image will be, and determines then your solution in contrast. So these are the components that you need. And if you translate it into some simple schematics, so you have your magnet, your arm magnet that you have your grading coils, or your induction cooker in this particular case, you have your antenna or the RF coils, and then you have some electronics around it. So you need some higher currents to get strong enough fields. You need some typically some higher peak power. This is a classical clinical scanner, and then you have some receive electronics to receive the signal, which we can also receive with the same RF coils. A computer that controls all of it, and that does the mathematics to do image reconstruction. If you look at this, then from the component costs, the magnet is the most expensive, and gradient RF is following, and IT is typically more affordable. So the strategy is, if you can somehow remove this magnet and make it cheaper, the rest gets cheaper, and maybe shift a lot into this IT domain to make the systems more affordable. So the classical MR technology, which is complex and costly, are this 1.5 Tesla clinical systems, and they use superconducting magnets that require liquid helium. You need a supervision system. It's a relatively complex sighting, and this is driving the costs. And this is one thing that it's difficult even if it would be nice to have, of course, open source, but even if it would be open source, not many research institutions would be able to actually reproduce it doing superconducting magnets. On low field systems, on the other hand, where you use permanent magnets, it shows that, you have a smaller signal to noise ratio, but it really depends what clinical applications you have. So for example, here's a 1.0 Tesla image compared to a 0.2 Tesla image. And if the diagnostic information is enough that I can see here where this arrow is, that there is something going on, and my higher resolution is not giving extra information, then it's perfectly fine, and I have a good workhorse, and I don't need to have this rocket in this particular case, but I get from A to B with my very simple vehicle. So this is also the strategy for the why doing it at low field, because it's possible, and using these permanent magnets. Now, permanent magnets, if you have a look at such a simple equation from a cylindrical magnet here, you have a radius of this magnet, and basically the magnetic field drops off very, very quickly. So this is this Z here. So you can either increase the radius, which gives you like huge magnet, because the remanence is very fixed. So maximum remanence you can get is 1.43 Tesla or something like that. So you need very huge magnets, and this doesn't make it cheap anymore. But what you can do is, when you have a lot of these magnets and you position them in a certain way, you have constructive interference on one side and destructive interference on the other side. And this is called a so-called Halbach arrangement. This is a linear Halbach, and then when you actually have it in a circular, spherical, or cylindrical fashion, then you get a homogeneous field inside. And then using not one ring but multiple rings, you can spread the region of homogeneity. And this is interesting because you can discretize this into this small magnetic material and make it basically a little bit more effective to use permanent magnets for this application without having a huge, costly, and very heavy magnet. And this is what has been then used for this low field project, so for this OSI² magnet. So this is a Halbach-like MR magnet. So it consists of 4,000 of this 12 millimeter magnets. And this is, again, a nice work from Leiden. And you can see, under this link, there's more information on how the design is being done. It has an inner bore diameter of 30 centimeters and a B0 field strength of around 50 millitesla. Yeah. The weight is now only 100 kilograms, so you can see there are already some wheels. You can push this thing around. It's not too heavy, and together with the electronics, we are way below 200 kilograms. So this is a much lighter and portable system. And this is something which, so this is on the left side is the system they first the magnet they built in Leiden, and then on the right side we built it together to take to Berlin. And so here you can see Tom and Wouter, which are experts in this magnet building, but you can see that also under, let's say, more difficult conditions and with non-experts that were building this magnet, it's all possible to reproduce it. And in the end, field mapping was done, which had very similar performance to this first magnet being built. And by the way, we're also trying to make the hardware that is actually used to build this systems, that it's also open source, and this Cozy Measure, this field mapping robot, is also an open source design. So you can put either your legs, extremities, or head in this system, and then basically it's mobile in a sense. So we just wrapped it, packed it into a van, and drove it from around 800 kilometers back to Berlin, where it's being further developed. So this is quite nice, and this works well. Now you could scale it up, of course, to other magnet designs. So here are some for extremities or even whole body. At some point, you have to ask yourself: is it worth this cost benefits performance? Because you will always have a limit with these designs to low fields in this let's say 0.2 Tesla region. But in principle, it's possible. Okay, so now once we have the magnet, we need our antennas or our RF coils as we have them in MRI, and this is relatively simple. So it's just a solenoid, you have a wire, it is wound. Then you have some capacitors to adjust it to the correct impedance. And then at low frequencies, which we are here at around 2 megahertz, we have a very, very long wavelengths, which means that we don't get any problems in B1 inhomogeneities, etc. We get very high B1 peak amplitudes for the input power. So this is relatively straightforward. And you can see that there are some 3D printed designs you can use to just wind this coils. Now for the Grannycall design, so for basically to get this frequency selection, there are different software packages, which this is a little bit more complicated because you need a certain linearity, and it calculates you the wiring paths for some conditions that you preset. And there are already a lot of different tools available. And here's an example of one of these tools. So you basically calculate the fields. Then from that, you can make the cut model. So this is FreeCut, for example, also an open source software. And then you can make your construction. And if you compare these measurements to the calculated fields, this looks pretty good. And a similar way for this OSI² system, you have this cut model of this X, Y, and Z gradients. So because you need it in all 3 directions. And then you have some 3D printing, you put it into this magnet. Then you still have a bit of cabling, which you need to connect. And later on, it looks pretty nice. So the 3D printer is very helpful. And of course, once you have this design digitally, it's very easy to share and then very easy to reproduce. So having the RF coils and having the graying coils, then you need to somehow send the pulses or make the synchronization between the RF and the gradients. And for that, you need some console. And here there are several options. So a nice thing is that you have so-called software-defined radios, which are used actually for a different purpose, but together with some open source software frameworks like Okra or Marcos, you can use them for MRI. So they all have an FPGA, and they have some RF transmission and reception channels, and can be used basically for the MR application. And this works pretty well. These designs are not open source. On top, this Red Pitaya, for example, is not an open source hardware design, but in parallel, there's also some work ongoing to actually have some dedicated open source hardware for this MR application, like here on the bottom left. So things are being used, things are being done in parallel to be used in the future. And because of this modular approach, there's quite some flexibility and then exchanging components if it makes sense. But this replica is relatively affordable, so this is not a big issue at the moment. Okay, we need some stronger signals than the red p-tire can output. So we need some amplifiers, and here's an RF power amplifier, way too powerful actually for this low field application. So it's 1 kilowatt peak power, and you can see it can be done over different for different frequencies. We have some good linearity there, and there are different designs. One done at the PTB, and then one is from Delft University, and the same for the gradient amplifier. There are 15 amps per channel, which doesn't sound much, but the system is also smaller, and the Grannycalls are smaller, so the amount of current needed to get a decent gradient field it is not that high. Okay, so once we have all these hardware components, how should it look like from the software side? As we intended to be, is that there will be an imaging platform. There are some first prototypes in this direction, and here you can see this is a scan hub. It has also a relatively modular approach, so basically you can select pulse sequences or MR pulse sequences, which there are very different imaging techniques. We get different contrast, etc. And then the trick is, so at the moment here is written this virtual MR device simulator, but at some point, of course, this will be the real scanner. So then you just need to guarantee that this format that the pulse sequencers are in is a hardware independent format, something like PulseSec or PyPulseSec, and then if you have an interpreter for your hardware, you can make sure that basically the software just selects your scanner, and this is being translated automatically to the hardware configuration that you're interested in. And then again, the same thing. So this would be the input to the MR scanner, and on the input from the measured data, you just guarantee that the format that you have is an open format, something like ISMR MRD, which is an open raw data format. And then you can push it into other open source image reconstruction software, which is already available. So they are much further ahead than on hardware side. So there are a lot of tools. And then, of course, once you have some standardized formats, you can also then use some open source post-processing tools. So nice thing is about having such an imaging platform that is in the cloud is you don't need heavy reconstruction computers locally, and you can connect also the community around the systems to further develop, but also to learn about this type of systems. So this is where the directions are going software-wise. Expected imaging performance. I showed this knee images before, and there was also a nice paper by Tom on some relaxation times for brain mapping. These are from the old prototypes. The new images look even better. Of course, I don't show you any of that here, but they will come relatively soon. So as usual, this all improves, but this is already quite nice. And now we need to see to see at some points what are then the clinical applications that can be used with this imaging quality. Now, the documentation. So what do I mean with open source documentation? So really like development files, electronic circuits, cut files, so everything that is as easy as possible to reproduce these systems, to repair these systems, to understand these systems, to customize these systems, production files, usage files, etc. We are way behind that. Yeah. So what you find under the link is we're working on it, but typically it's always the most difficult part, because it's still the least let's say fun part. You typically like to make something new and then you document, but this is something we are working on. And of course also the software. And one new thing. I will talk about this briefly later. It's the regulatory approval, the documentation for regulatory approval. So nicely, we got funded a bigger EU project, which starts next year. And part of it will be also to provide documentation for regulatory approval. And this is also something that doesn't exist in the public domain. So there are no blueprints. It's extremely valuable, not only for this project, but for other projects, just to be able to copy that, because then this bar of entry to the market will be much, much lower, which means that not only more innovation, but also products should be in theory cheaper, because it's easier to get on the market as to the current case. So this is all ongoing, and we are quite excited that we already at this stage, and that we can continue. Also, we could secure some funding to continue this, and people get more and more interest about also this concept of doing things a little bit differently and collaboratively. Okay, I will not talk too much about the licenses, but just the slide that you see is what software and hardware licenses and documentation we use at the moment. Okay, and I will jump to the next point, to why low-field MRI. So apart from the argument that we can do low-field MRI, so there's also a need for low-field MRI, or an opportunity for low-field MRI. So it's not only that we target this because it's doable, and then there is no clinical need. So there was actually some recent interest in this low-field systems, and it came very strongly also with this. So basically, there are two field strengths that are interesting. One is this 0.55 Tesla, which was a very nice paper here by Campbell Washburn. And this, for the first time, was really like a comparison of some high-end equipment with some high-end equipment, and not only some, let's say, I mean, the current clinical and research focus is on high-field MR systems. And if you do a comparison to systems where there's not so much resources put in, then very often this comparison unfortunate. But here they made a comparison of really trying to see how far you can push the advantages actually that low field has over high field, in terms of some safety things that are more relaxed, or some susceptibility artifacts, to some clinical applications. So you can see here, for example, lung imaging, you have much more contrast than compared to 1.5T. Yeah, and this is one of these very nice examples. And another example is this is going one order of magnitude below. So then to not 0.55 T systems, but 50 millitesla systems. So this is the same field strength that the OSI² scanner has. And this changes a bit the perspective of how MRI is being done. So these are now point of care low field systems, or portable systems. So you can see here the first one on the market very recently, and this is the Hyperfine system. And now the MR is pushed to the patient and not the patient to the MRI. So this changes completely. And now they're using this in intensive care units for stroke, stroke detection, etc., or stroke monitoring. And this is interesting. And such a system weighs now 600 kilograms, and you have a little joystick and you move it around. Yeah, and there are some images here on the right, and there are quite some studies already published on the diagnostic performance. So this is something very useful. And here's another nice paper from a similar system at around this 50 millitesla, which shows also some 3 Tesla images in comparison. Yeah, so you can see or can get a bit of a grasp of what is possible at this field strength, even though it seems initially very low. But again, in the end, the image decides if you can see what you need to see to make a proper therapy. And here you can see a tumor, patient with a tumor, a different contrast to different imaging techniques, also diffusion weighted imaging, etc., and comparing to 3 Tesla images. And in these images, you can clearly see that there is this tumor, and you could probably also very well determine the size of it, etc. So there's plenty of information, even in this low field regime, which needs to be explored. Another advantage is using imaging of implants, and this is also something that at higher field strengths gets more and more difficult because of the susceptibility artifacts. So you can see the at 1.5, 3T, or 7T, how big this unimaginable part is in this image around this implant. Yeah, while at 50 millitesla, you can pretty well see this screw here or the stent. You can see barely, but this is also something that I think for a lot of applications it might be quite interesting, and in particular because we are getting more and more of these implants in our bodies, and this will be independent of low field, high field. This will be a challenge for MR imaging in general. And then on the right hand side, there's also a patient with the screws, also the comparison of this 50 millitesla regime to a not 100% sure if this is 3 Tesla. I think it's 3 Tesla, where you can see much stronger artifacts. Another thing is portability. Yeah, so not only in an intensive care units in a hospital, you push this to the patient, but even further, you might drive the MRI to the home of the patient or to remote regions, which is also very interesting for many applications. For example, I mean, stroke, you typically need very quick assessment within hours on the condition of the patient. So that this might be quite useful. And here, for example, they packed one of these Hyperfine systems in a van and did some imaging in there. And here's another a nice work from the group in Valencia that they used also this system in different conditions. And the last one is actually at the patient's home. So this is also something that might a bit change and might be an opportunity to investigate different imaging applications. For the portability of the OSI² system, to jump a little bit back to the open source component that we are very much interested in. So this year there was this the ISMRM in London, and so basically I went over from Berlin to Leiden, where we packed with Tom and Wouter, Tom O'Reilly and Wouter Chevers, we packed this OSI² system into a small van, and then we drove onto the ferry. You can see the magnet there. Then we had a session at the conference, which was very well visited on build your own open source MR system. So it's also nice because within the MR community, these things are also more and more appreciated and arriving. And it's not only software, there is a much stronger hardware focus also from the study group of engineering, etc. So there's a lot of support and interest, and this is being you can also see by the participation in the session. And then we had another demo which was more in the hall, which however we were not allowed to do very long, because then we had to escape. So escape route, keep clear. So the interest was very big. We did that a little bit spontaneously, but of course we couldn't plan that. So just a little nice gimmick here. Then we put it back into the van and drove back. But in principle, this works. You can drive around with your MR system. Okay, good. Then I will jump to the last but not least important part, and basically why we do this open source. And there are many aspects that we could have long discussions of why that's pretty good to do in terms of reproducibility for science or education or cost efficiency, etc. I will try to pick up some examples, and then if you have some questions, we can discuss it later. One thing that I'm copied a bit from Joshua Pierce's very nice presentation, which I really liked, this idea, and it's about funding. So if you see if it's medical care or healthcare or science, if you see this as you always have an endless amount of resources which you need to distribute relatively or distribute in a way to maximize impact. So how can you do that? And for example, if you have this $1 million and then you have the current standard model of distributing it to researchers. So you have some funding scheme where people are applying, and typically like 10% then gets this application through, which the others are of course not very happy. And in this particular case, the old white gray-haired man that has already the resume gets the money. And this continues over 10 years. When you assume, and this is also something that we have also made this experience, that you have open source hardware that is typically 1/10 of the costs of proprietary hardware. So like laboratory hardware, I'm not talking about medical devices because they don't exist yet, but just 10%. So if you make it a condition that this design is an open source design, then in the follow-up year, you can have 10 more people in having this design, rebuild this design. And of course, along the process, you get much more innovation, many more research results, many more happy faces, so to speak. And so probably it's a much better way to invest in science and to get scientific output for the same amount than in the current model. And these are also this open science initiatives that I talked about briefly in this current funding schemes. But we are not there yet that it's really mandatory to have it open source, but it would be nice. And then seeing it from the healthcare perspective, we also have to ask the question, I mean, we do have increasing healthcare costs. It doesn't matter where you are, they will be increasing. And we have an aging society. We have monopolization in many healthcare sectors. So we really need to ask if the technological innovations, this is our current approach, if this is something we want to continue following in this model, if this is enough to tackle that. And to show you an example of the cost of ownership for MRI, so you have here this 1.5 TMR systems. And if you take the cost over this 10 years, so it's not only that you buy the MRI, which is maybe a million or a little bit more, but you also have to operate it. So you also pay for this, maybe some 10% of the purchasing price. So then you have a certain amount over the years, and then an innovation comes like low-field MRI, for example, that got a little bit of a boom recently, like this Hyperfine system. And yes, it's cheaper, but it's also not that cheap. Yeah, so these are still this old prices. I think they went also up a little bit, but you can see, so you pay a bit less, but you also pay a bit less for what you get, not for the functionality you get. So from this 10% I talked initially about, 10% of the cost. So there's still a lot of room there. And if we look at this OSI² system, which is a similar field strength, and assuming we can get the same image quality, at the moment we are material costs of 20 to 30K roughly. So now the question is, and we do believe that there is enough room, even with a standard business model behind it, to have these systems for a target of less than 100K for this 10 years. Yeah, and this then makes a substantial difference, because again, you're talking about a transparent system which you can customize, which you can repair, which also the markets can adjust locally to that. So this is much more flexible, and let's see if, how this will end. But this is one example of this trying to approach it from a different perspective, to approach this problem of unaffordable healthcare. And here are some other numbers, something similar, but we took data from the German healthcare system and basically replacing a design that you can calculate the numbers with an open source design. And the bottom line is we have public healthcare systems, so which potentially can save a lot of money by an open source approach. So why not reinvesting that to save it in the future in this in particular sense? And we can collaboratively work, of course, to improve the systems with a much larger community. That typically even a big company like Siemens or Philips, they also heavily rely on the scientists across the globe for innovations. And for even smaller companies, like in this low-field regime, this will be even more difficult to just do everything by themselves. So there's some opportunity. And the same for not only for the device market, but also the service market, that if you have the knowledge about the system, then you can do in-house maintenance, or there's more competition around this maintenance contract, because it's understood, the risks are well understood. And then if you can only lower it by a few percent, assuming that you cannot build the devices cheaper than what's currently done, but still you save a lot of money for the public healthcare system. So two big arguments, and of course it would be nice. Okay, access to MRI in the European Union, very different. Yeah, so I had recently some issue. I had to wait 1 month for an MR scan. I'm in Germany, so we have the highest or one of the highest within Europe. So I don't know how long I would have needed to wait in a different European country. And then the question is it still on time to get this information, this diagnostic information? And then looking at across the globe, I mean, even if we put on low-field system in there, this would be like reinventing MRI, because maybe it's the first system that is being used clinically. So this is heavily unequally spread. And this is also one of the motivations of this project, to actually change that. And here we have to ask ourselves, are we doing high impact research? And taking this example, because this is very, very theoretical, but just like, let's make it very specific. So Berlin, 3.6 million people, 125 scanners, Mexico City, 9.2 million, 13 scanners, and Senegal, nearly 16 million, 2 scanners. So we go to the conferences, we are motivated by other researchers to do research. We are an international society or a community, yes, but we are not really doing international research because we are always within the bubble of our resource-rich environments in Europe or US, and this is so to speak, it's only international on paper. So what we then, for example, do is and focus on things like doubling the speed of an MR scan. But when we look at the distribution of the beneficiaries, it's of course very much heavily in direction of the places where the scanners already exist. If we would be able to make the machines less costly and focus on this part, we can not only reach more patients, but the distribution is a little bit, the balance is a little bit better. And this is also something an open source approach can do or can help doing. And here is an example of one of the builds this summer, actually in Uganda. So Tom and Wouter, they packed such a kit, such an MR building kit into a box, and then shipped it to Uganda. Arrived in a small van. And then they did what I wrote here, true technology transfer, yeah, because they did the local builds with the people around all the components, and this is the best you can do. This system of donations doesn't really work well. You need access to information, and there are smart people. They can understand it, they can build it, and they can adapt locally. And then within this build, for example, there was also Josh Harper from Paraguay. So he's also interested in to do it in Paraguay. And then you have the next person trained and able to then spread or scale up this locally to their own environment. And then after a few weeks, so they managed to have this set up and to get the first image of a bell pepper. And a lot of happy faces here, and particularly Jonas Obongolo, who's the director in Mbarara University in Uganda. And now he can, of course, continue either research, combine it clinically, or even some industrialization of it to get some products. So this is really impactful work. Okay, in other fields, you maybe saw it or also in some of the LibreHub seminars. In microscopy, we have a huge spread from high-end devices like the best microscopes that are open source designs to the cheapest microscopes that are based on open source designs. So this is something really nice to learn, and we're at the moment scaling up, but of course a microscope is different than an MR machine. I just wanted to show you what's already possible. Ultrasound, a similar nice example, because they also started with an open source community. This one is Open in Paris, and some similar components like we use, by the way. So here's a red pitaya, and some first prototypes, some first images. We had also had to get together with them in Paris when the ISMRM was there to exchange experience between the communities. And then they continued. So they continued a little bit the classical way. Then at some point they for now they closed it down and they went to a product. And this is still a success. So I do think I do need to get updated, but I do think they launched the product already. And I'm not sure, but could be that once they have the next version, then maybe the first version will be then shared as an open source design. Let's hope for that. This would be, of course, fantastic. But in any case, this is also a success of coming out of such an open source community. And also another example from software, which there's a poll that was being conducted on open source software for many different years. And initially, one of the most reasons to actually use open source software was this freedom of vendor lock-in, or the affordability or cost, because you can download it, etc. But this changed, and open source software is a multi-billion-dollar business, and there are commercially available solutions, and they coexist with the open source part. So it's nothing that is really contradicted. And interestingly, after some years, the most important reason for this companies to actually use open source software was the quality of the solutions. And this is also one thing that I also do believe, that if we have designs that we as a research community, for example, can focus on, long term we get much better results than in this current model of just having this prototype and then it's being closed down, and then it's very often reverse engineering to get the information you need. Okay, so looking at our timeline, I'm nearly at the end of this presentation. So we started very naively, some let's say 5, 6 years ago, to say we want an open source design. It somehow worked out that we are now here having this first prototypes, which to be honest, I haven't believed that this would have been so fast. And now we very naively say again, in 5 years' time, we are in the clinic with open source devices. And of course, there are some things to be still done. A certification process, a business ecosystem. It's not that everyone wants to rebuild this components. You want to have products, and for products, you also it's nothing that you customize all the time. Yeah, so you, of course, you freeze a version, and it has to be safe, and it has to have good quality, etc. But still, the core is understandable. It's transparent. It's characterized, and this can be a huge push for innovation in products, and also to reduce costs. So I mentioned that we will be working on trying to scale up now the current progress to more institutions, to have really the same systems that we can continue developing collaboratively, but also involve more people around it. And part of this, we will also provide the documentation according to that is needed for regulatory approval. We will not be able to provide all of it, but as much as we can. And then we can think also of some strategies that are already partly implemented, but a lot of this information never sees the public domain because of the current model. When you invest and you keep it close, this is your asset. But how to combine this with for example, Git type repositories and open source hardware documentation, and then together with this MDR part. So this is quite interesting, and also as a blueprint for other projects that, for example, have similar risk categories like ultrasound or like maybe other imaging components, or also other medical devices that can just see what is needed and which structure is being applied, etc. There are no real blueprints at the moment. And then, of course, there are other aspects that are quite interesting. If you have a fully characterized systems, that you know all the uncertainties, and uncertainty propagation, for example, in deep learning is a big topic. But also things like quantitative imaging, or to make things more automated. So the more information you have, and the more people can investigate and find solutions for the current problems. Also, and especially in terms of AI-based stuff on efficiency, robustness, and explainability. I think that this can only help, and keep it closed doesn't make it easier. And of course, simplifying things and the collaboration with industry partners I already mentioned. Okay, with that, my time is up, and I will. I hope I could show you a bit this, what I believe is a stronger approach towards more collaboration than competition, and not necessarily out of necessity, or a strong necessity. Of course, it's a necessity, like in global warming or COVID, but we saw like this approach is how potent they are, and for medical devices, I think this is this makes total sense, because it's not optional, it's needed, and there are so many public healthcare systems. Why is there not more a collaboration on some essential technologies? And then classical upload your work, open source. It always helps, not only in low-field MR. There are a lot of different areas where I think it's very helpful for students to not to reproduce the status quo, but to really continue on science. There are some policy briefs you can use to convince your institutions. From for example, good one is from Gosh, or you can find here. And if you have some more information, you have some more questions, you can contact us. Okay, so with that, probably I forgot some logos, but there are I'm just representing a big group of people here. It's not my individual effort, and it's fun, it's useful, we're progressing, and we still have big goals, and it's cool to see that it's happening. So thank you for your attention.
Thank you, Lucas.
Amazing presentation.
Very interesting presentation. We are kind of like at the end of the time, but maybe we have a few minutes for a couple of questions. So anyone wants to ask?
I would like to do so.
Okay, so Guido first and then Vicente.
Okay, so first of all, thank you, Lucas, for your presentation. I'm actually working on a similar project right now, and I would like to ask you, well, I have actually two questions. I hope they're not too long. So first of all, you mentioned that the RF antenna has some capacitors in order to assist in the impedance matching. Could you maybe elaborate on that?
Yeah, so I mean, for the low field part, you just have the standard solenoids, no, and then you can put capacitors at 2 positions. One typically you need for tuning matching, no, so you have to adjust your impedance to get a maximum power transfer. So this is where you typically have a fixed capacitor and then a trimmer capacitor that you use, and then you can in addition, then you can segment also a little bit the solenoid along the length of the solenoid with some additional capacitors. But yeah. Mm-hmm.
Okay, thank you. Next question is, so you mentioned that this system has not a very good signal to noise ratio. So I also wanted to ask if you had some sort of techniques or anything special that you needed to do in order to reduce the noise in the system.
Yeah, so that I didn't show it. I removed it from the presentation. But there are so there are several things. I mean, one is the classical lower signal to noise that you will have eventually, which you there are different techniques how to deal with it. So we also investigate some deep learning based SNR enhancement. And probably with different imaging techniques, which is also not yet completely investigated for the low field part, like what's best and how much you actually need. So this is what you can do there. And then there is another thing which is more disturbances. No? So once you have this portability of the system, you have more electromagnetic interferences. So you're not anymore in an RF shielded cage, and also RF shielding at a low frequency is a little bit more difficult. So you will get more noise from other devices that are surrounding the MR system, and how we haven't done that yet, but there are some works that did investigate this. You can use pickup loops in different positions of the MR system, and then you can use different techniques. For example, also some deep learning based techniques to get rid of the noise, and this looks pretty nicely. So the images without that, you can barely see the brain, and after that you can barely recognize this noise. So it can filter more than 90% of the noise. So this is pretty nice. But of course, it has to be also tested outside of just the research paper, and also in the real in real clinical settings, because there's a lot of different devices, a lot of different noise sources, but also things like temperature changes that could affect your portable system, etc. So still many things to do, but yeah, it goes a little bit into to answer your question.
Okay, thank you, Lucas.
Thank you very much.
Thank you. Yes, and I want to thank Lucas for a very interesting presentation. So I understood from your talk that you proposed this model of open source hardware MRI system as something that will be useful clinically for patients, for example. And so I wanted to ask you, do you think that this is something that will be interesting for existing MRI companies, say, for example, some of the big three, given that this, I think you mentioned that this device would basically cover availability for areas or resource settings that are not currently covered by other competing systems like the big commercial ones. So do you envision that this business model will be attractive for some of the existing MRI companies, or otherwise, who will be the one who funds this? Do you think it will be government or volunteers?
Yeah. No, I do think that in general, this low fields, the one that I presented more, this 50 millitesla region, this will be something where in the next years there will be a couple of companies coming on the market. And then, of course, we will see after a couple of years later if they will stay as independent companies or if the bigger ones will acquire this as part of their portfolio. I don't know that. I do see there is a need for it, and there is an opportunity for it. And then, but it will also depend on the costs. That's because there were low-field systems already for a while on the market, and then and they have some niche applications. The question is how broad will it be? But I do think that having an open source system and being able to evaluate that with a broader scientific community on systems that everyone, or not everyone, but in principle, a lot of people have access to and can transparently work on, I think that's the highest chance to see what the potential of the technology is. The other low-field segment, which is an order of magnitude bigger, this is something that the big three are interested in. So they are working on their own systems. And I think they are monitoring the lower field segments of this Hyperfine system carefully. And I'm sure, I know they have some interest in that. Let's say it like that. But of course, they don't. I mean, classically, they will have a conservative approach because they don't need to. I mean, they have their position. They don't need to leave it. No, so. But I do believe there will be a little bit more diversity in terms of companies on the market in the future, and then we will see from that also which applications will grow out of it. But I mean, thinking of this open source approach, and if we can really make it, if it can be a product in the range which currently an ultrasound maybe costs, like not a cheap ultrasound, but a higher-end ultrasound. I mean, then it's something that you could have this in small doctors' offices, and if it's made in a way that you don't need the expertise and it's just a push-button system, there's a lot of information that you can gain that is currently not in the healthcare structure because it would cost too much money, too much effort. But it could be established with having this cheaper systems, and then if you still need a higher resolution image with more information or other techniques, you can still go to a better MR system. But it doesn't have any radiation or any other side effects. It could be probably done much cheaper than currently is. So I do see a lot of potential for the technology.
Okay. Tobias?
Thanks. Really amazing presentation. I have a comment and a question, and I'll start with the comment. Just as information sort of for all the participants here or people that will watch the video later, that it's good for you to keep watching also the space of the Libre Hub project, because under Pablo's leadership, there will be more MRI related, open source related seminars and also workshops. So of course, this is still not completely finished and organized, but we hope to bring you, Lukas, also to Chile at some point for one of those workshops. So there'll be some opportunities for that. That's the comment. And the question would be related to the reproducible. So I was excited to see that you're using that as well, or I've already heard about it before that you're using it. I use it also for something like a flow cytometer setup, and I think there's an opportunity. I was excited when I found this board because for me it was a very accessible way of using an FPGA in my setup. It's a not so expensive and quite sort of available component, and it's a pretty open framework, and you can use especially Python, so you can develop your own open source software without license payments around this. But you said that there are also some limits for you, so I was just wondering if you could extend a little bit your reflection on using this board in your context.
Maybe yeah, so I have to say there are few there are some things in parallel also to overcome the current limits. But for example, one limit of this red pitaya is maybe the amount of channels that you have.
Yeah, absolutely. I got already sort of beta level access. I already have this multi-channel system now, but that's also, yeah, it's not so scalable, I guess. So now I have 3 red pitayas together, so they have 6 analog inputs. It's still not that much.
Yeah, exactly. But I would say this is probably one of the biggest drawbacks. But there are some efforts to daisy chain, a couple of them together, and then we will see. And in general, I do think that because the red pitaya is not designed for MR application. So if you have something more customized, but of course you would also need the community behind it to drive that. So if not, then it's probably better to have something proprietary that works and that you know that you will have next product or some support than going for an open source design that has no community and then dies off in a few years. So let's say for this part, we are also observing it. We are observing what's. We're also not sure what would be the final console. I mean, for example, we will test for ourselves. We will also test some other cards we have, some arbitrary waveform generator cards we have, which are very flexible, can be connected over PCI Express, and you can just, if you need more transmit channels, you just buy a card. Plug it in and that's it. If you need more receive channels, you do the same. So for research purposes, that's pretty cool. But for this, let's say, affordable system, I'm not sure yet. But for example, the Valencia group, they're using the red pitaya for their low-field MRI systems, and they are pretty happy with it. So, but we don't have any experience yet of comparing it to different consoles and to really check the performance. So we want to do that at some point, but we haven't done that yet.
It's on the list. Thank you.
It's there's a long list. So
yeah. Thanks.
Okay. So I think that we ran out of time actually a few minutes ago. But I would like to thank you again, Lukas, for your time, and to all the participants. It was very interesting talk and questions. So thank you very much. And hope to see you next time. We'll, as Tobias said, we have this series of seminars in different topics, and you are all invited to participate. Okay. Thank you. Bye, Lukas.
Thank you very much. Bye, everyone.
Thanks.
Bye.
Bye. Thank you.
Hasta la próxima.
Yeah.